density and then conserve momentum for the velocity components. The same thing happens when we transfer information from the finer meshes to the coarser ones. But in this case, that's a much simpler thing, as we just make an average of the values which we have in the fine mesh here to the value in the coarse one. I don't know if you can see it here. This is a coarser mesh, and then it was subdivided into 4 fine meshes. So then we have here 4 different values in the 4 fine cells, and then we just average them to the value which we will have in the coarser mesh when we make the information transfer. The same thing here they do to the velocity components, but in this case you must be more careful because that's a vector quantity. So then you must conserve it in a slightly different way than you do with a scalar quantity such as density.
But that's something we don't probably need to worry about, that, right?
Because it's a non-conservative code,
yeah.
Right? Yeah. But still, I mean,
no, you do.
You want to pass?
You still need to go through the hoop of making sure that you're. I mean, the time-stepping routine is non-conservative, but this interpolation is a sort of. It's almost as if you initialized a new. At every time step, it was a new initial condition, right?
Yeah, but you don't have to you don't have to do that.
On the pencil code?
Yeah.
You mean that we don't have to worry about the fact that we are passing the
you have to worry about
amount of mass?
Yeah, maybe not. We have to worry about accuracy, right? So you want to make sure that whatever interpolation we do it to 6th order. And high accuracy should, of course, conserve mass to a high accuracy, but it shouldn't conserve mass to infinite accuracy.
It's the point that you do the interpolation in momentum space, do you, and not in you don't interpolate.
Yeah, but that's not what we do in the rest of the pencil code. And we don't have to.
You never do an interpolation in pencil code.
Yeah, but we could. I mean, what's the problem here? We could do whatever we want.
There's a significant. The type of error you get in an interpolation of row U is different to the.
Yeah, what I said. I mean, we still do it to a higher order. Are you actually thinking of interpolation in low order now?
I did it once, and it was with low order. Yeah,
that's of course crazy. I mean, you have a high order code, and all of a sudden you do. Okay, let's do something at very small order. But let's do it. Let's make sure that at least some things, which somebody could perhaps check, are at least 100% correct. I mean, that's of course a philosophy that has been adopted elsewhere.
Okay, yeah. So that's one of the things that we learned here from giving a talk, that everything has to be high order.
Sometimes it can't be high. I mean, can you make that arbitrary?
You can do 6th order interpolation.
No, Anders is asking about.
But you need 3 points.
I mean, but somebody was saying we don't do interpolation in the pencil code. But what do we do in the shading box simulation?
Well, you do have it, but on the nested mesh, just like you have a ghost zone in a real problem, the actual first 3 points of the nested mesh are not really evolved. They're held. So it's still the ghost zone is on the nested mesh also.
Okay, and
then you have your 3 points for interpolation. Okay, that's what you're looking for, right?
Yes.
So what?
But actually it's 6 because you've got your ghost zone for your derivatives and your ghost zone for your interpolation. So your actual evolved patch is a tiny thing.
I don't understand, but you realize first of all that we do use interpolation in the pencil code, right? In 6th order. That's 5th order. For the sheet boundary.
Of course, yes.
You have to, right?
Yeah.
We have to.
Yes, and that's high order. It's not conserving anything, but it's as accurate as possible.
Yeah, sure.
And do we do it?
Unless you, Wlad, you know that.
Right.
That we have the shear and sheet boundary condition.
Which does the interpolation array.
And sheet boundary condition?
Yes.
Oh, I didn't know about that. Good. Yeah.
So something, by the way, this is another issue of the pencil code. We have all kinds of things in the pencil code, and then somebody doesn't know.
Yeah,
there's just so many things.
Would that be because there's no documentation? Let's let Wlad have his talk, because we discussed that yesterday at length.
Hands up, who doesn't know that there's a temperature module? So nobody.
All I meant is
Not even two. But actually more interesting. But the thing, you may even know that there's a temperature module, but who thinks actually that the temperature.f90 module actually works?
Who thinks it will work?
Doesn't.
No. Completely outdated.
It's not.
It's probably 4 years old or something. But there's the temperature underscore ionization. Which
right.
Who believes that works? And then we have hands up again.
Right.
And so in order to do a temperature without ionization, what do you have to do? You don't use temperature
Pretend LMTT.
You use temperature underscore ionization with ionization equal to 0. But if you put it to 1, it also doesn't work, right? It is not 1.
Yeah,
do you know
then
why?
you get negative pressures.
No, but that's just something we didn't put into Bugzilla yet, right?
But why doesn't it work for? Why?
You can
You get a negative pressure. That's why you can't have.
No,
But why doesn't it work?
to use fixed ionization with the temperature module, the temperature underscore ionization module, in such a way that that y is equal to unity.
Yes.
It's because you get negative pressure.
No. So what's the problem? No, you don't. You don't. Okay. So why?
Well, of course you don't. Well, that's because you can't. But that's why it doesn't work. Because the internal energy is the heat energy plus the ionization energy, and if you've got plus a constant.
Sorry, you're wrong. Sorry. You don't get negative pressure. So what's the problem?
But that's only if you have negative ionization. And if negative ionization is smaller than -1, right? Then you probably get something.
That doesn't even make sense. Then negative ionization.
Yeah, but that's the only way how you can get.
Well, no, it's that if T equals 0, you still have pressure,
That's what we have.
right? Which is the weird thing.
Yeah.
That's the problem.
Right. Like this, right?
Sorry, don't take the temperature.
No, you don't. Because y is 0 if T equals 0. Y is 0 if T equals 0, so you don't have any pressure at all.
P equals NKT. T equals 0, P equals 0. No, it's not relevant at all. Poor Wlad.
No, it's 6.
No.
This is a copy of the
It's fine with the pressure, really.
You're receiving mine, yeah? Right, so let's keep going. Right, so then here, what I have is that we must be cautious with the interface between the finer grid and the coarser grid. Because then here we will have cells from the coarser grid which will be ghost cells to the finer, right? So then that's an important thing how to treat that. And in most codes, that's not a big issue because they have a simple time stepping thing. So then they can do it with say 2 or then 3 ghost zones. But in the pencil code, we have 6th order. But in the pencil code, we have a scheme which is 6th order in space, 3rd order in time, right? And then we need at least 3 ghost zones per time step. But as we have a third order in time, we need at least 9 ghost points for the final group, which was just too much.
Yes, right, for the different time, yes.
Yeah. Tommy is looking at me like, what the hell are you talking about? You don't follow.
Yeah, you need a blackboard rather than different slots.
Yeah.
I mean, this has to do with the fact that we have 3 different time levels, of course. And then the time step of the final mesh is, of course,
Twice the time, half the time.
half the third, of course. So you do the time from one time step to the next, and in the meantime, the small mesh has to do 1, 2, 3. And so it has to calculate the values in the ghost zones. That's what you're saying, right?
Mm-hmm.
So it has to have ghost zones, 3 ghost zones here, 3 ghost zones here, and 3 ghost zones here. Maybe even here. So that's 9.
You don't communicate.
No, that's
You don't communicate the nested mesh. Why? I thought you were using the F array, and the F array is communicating at the end of a time step, whether it's a nested time step or a full time step.
Well, the main thing here is, well, this one here, right? You have here your mesh.
Should we move this up? Should we move the screen up or something?
Okay.
Or not?
Well, see it here in 1D, right? Here, that's your cursor one, and then here, there's a finer, okay? If you wanna advance this one here, the finer, you have to feed ghost zones, right? Pass here ghost points to the
Good, at the edge. You're using an F array by
advance it, right? But the point here is that you will do it 3 times per time step. So then you have to hit it here 3 times while it is evolving. So then 3 times 3 times per time step, right? And then you need 3 points in each time step for the solver. So then 3 times per time step.
Oh, that's fine, right?
I don't know. 3 points per.
But you communicate at every time step, right?
Yeah.
Yeah?
No, you actually communicated 3 times per time step. No, yeah.
Sorry, what you do?
Communicate once.
We're talking about IT order 1.
Yeah.
Right? Okay, so a time step is a time step. We don't have to stop time step to time step.
Sure, yeah.
In one time step, you communicate at the end of the time step.
See,
Now, on my nested mesh, the outer 3 points of the whole nesting, allowing for the fact that this nesting is, of course, parallelized in the same way as the code is, has that outer boundary does not change at all during my substepping of the smaller mesh.
yeah, true.
Right?
Mm-hmm.
So that bit stays fixed, but the internal boundaries of the thing,
Wow.
Oh, I see. You mean you can't reinterpolate?
Yeah, that's
Of
right.
course, you can't reinterpolate.
Yeah. It's going to be like time 0, right? And then your time equal to, well,
The boundary condition on the nested mesh actually changes.
yes. Correct? During nested step.
Yes.
Tony, t equal to t plus 1 time step. We have here like 3 points, right?
So I understand the principle, it's just I didn't see why you have to do it. But that's it.
Yeah. So then you will calculate the finer mesh 3 times here. But you can only communicate here and here. And then here, it will need 3 ghost points. Here, more 3, here, more 3 points. So it can evolve. So then you must feed 9 points here on this. So then this one here will use the first 3 points. That one here, the next 3 points, and then that one here, the final 3 points. So you need 9 ghosts. I will use to test that.
Agree.
I agree.
Sorry?
I understand. Yeah. Okay.
If you want to take the derivative 3 times without applying the growth zone, you're going to triangle.
That's the point. So, I am going to show you right now what I did with the professor code.
I don't understand why you put it.
Yeah, exactly.
Did you want to assume that
Well, exactly. If you assume the outer boundary, then the ghost zone of the nested mesh is frozen in time, is frozen on the time scale of the nested mesh, then you don't have to do that. But this somehow lets you evolve it.
but you would have to
Well, you have to
assume
because you have to
that
hash stuff out. The way it moves out, so that's the growth big curve. It's about change.
Yeah. Yeah, it makes sense.
So, now that we all agree that we need that, I can show here. This is a simple 1D problem. Oops.
And can you move? We can move the projector.
Oh, sorry. Here, it's a bit hard to see, but that's a simple advection problem. And here we have a coarse grid, and then in the middle I am adding a fine mesh. So then here you are seeing how many ghost points I am needing for the fine mesh which we have here. On this problem, you can see quite well what is going on. But if we make a comparison,
Are these 9 points or how many?
actually here I put more points. I put 18 points. I don't remember why.
For the ghost zone,
Yeah.
on each side.
Well, yeah, I did this thing almost 1 year ago, and I looked at it now like 5 minutes ago, so I don't know exactly what I which I did in the first time. But sorry, here that's a comparison, right? We have here how it looks in a simple grid, and here that's the fine grid which I added to that one here, and the final nested grid after we communicated the finer grid with the coarser one. You see here that we have a much better sampling in the regions here where in the coarser mesh we just have wiggling. We still have wiggling here, but it is solved with much less viscosity than what would be needed here, which is a good thing. And here, that's the difference of the single coarse grid to the nested grid.
I mean, we do want to have more viscosity in the coarse mesh, no?
Yeah.
So you should never have actually bigger.
What I'm saying is that if you use nested grids, you don't need to use too much viscosity in the finer grid, which is the thing that actually make your solution better in the finer grid.
When you evolve the coarse mesh, when you evolve the coarse grid, do you take the mesh points that are going to be replaced by the finer grid into account of the time step for the coarse grid?
Can you repeat, please?
When you calculate the time step required for the coarse grid, do you have to, or do you need to, I don't know, do you take into account those points in the coarse grid that will be replaced by the fine grid?
Yeah.
And must you, or is that, and is that a requirement, or is that a...
That's a requirement, right? I mean, the two grids here, they will be evolving independently.
Yeah, they would be out of sync otherwise.
Huh?
They would be out of sync otherwise.
Yeah.
Well, no, do you not, I mean, it depends which way around you do it. Do you not surely, it seems strange to have the coarse grid confining the finer grid when the finer grid knows a lot better. So do you not shouldn't the time step be the other way around? Shouldn't you actually evolve the fine grid first?
No.
And the first step of the fine grid, and use that to determine the time step that the course
So
grid
you
will
evolve the course grid first. You evolve the course grid first, and then you see what is the time step, right? And then say, if you have twice as much resolution in the final grid, means that the time step for the final grid will be twice smaller. Which means that you will evolve the final grid twice for a single evolution of the course grid. Does that answer your question?
I mean, you've answered what you do, but I have an objection, because if you do these 3 time steps of the finer mesh, if you've advected some wave in the finer mesh, you've advected it 1 time step, 2 time steps. By the 3rd time step, the time step required to evolve that 3rd time step might need somehow to be smaller, right? Or not? Or do you do the same as we do with the Runge cutter, that you assume you can apply the same time step? I mean, that's what you're doing. You're doing the same as the Runge cutter. It's just where it was being applied for 3 sub-time steps before, it's now being applied for 9 sub-time steps.
What you're saying is that the final grid knows better what is the speed which we have there, right?
Yeah.
So then, therefore, it should be constraining the time step.
Indeed.
Not the course grid.
That's somehow what I imagine. Yes, it knows. You'd think it would know better in that region.
The fine mesh. The fine mesh.
Yeah. It should know better how to constrain the time step.
There's no problem there. There's no problem.
Except that it's
Except you could be over or under constraining the time step.
I mean, you're still saying the time step length is controlled by the course mesh.
Yeah, no, but I mean, letting the time step be controlled by the fine mesh, there's no implementation problem at all.
No, there shouldn't be any difficulty doing it.
No.
Except you've got to do the steps out of order. So you have to do the first one of the fine mesh, then the coarse, then the fine, and the fine. Or something like that, right?
Mm-hmm.
Or you have to do, yeah.
What is that? No, why don't we do the fine one first? And then
Because remember, we don't actually know what DT is until we've at least gone through the motion of doing the first sub-time step.
But then how are we going to evolve the final mesh first if we need ghost zones which are fed by the course grid?
You use the evolve? No. Don't you do the interpolation at the beginning of the time step?
Actually, it's done after the two evolve to the same time. So it's done in the end of every time step. That's when we actually...
But you put it back again.
Yeah.
But you actually interpolate onto the finer mesh at the beginning,
Yeah.
and then you interpolate back at the end.
Yeah, but that's true. I mean, it could be done. So I mean, you could evolve this first, and then you make a communication here to there. But then,
because unlike other codes that do this, time step constraints are a critical thing in the Fantasy code, right?
the point is that
You really need to know.
the way that is being done is this. You know, I mean, say that this one will evolve to a time 1, right? So then this one here will make 2 time steps, so we can get in synchrony with this one.
Yeah, sure.
Once again, what you're saying is that I should make it evolve twice, and then I go here, make it evolve once afterwards.
Well, sort of, yeah, effectively, yeah. Exactly.
I don't know if
That's the standard pruning.
I think that's normal.
no, that's actually the opposite. Then the way that I see people doing is that they do the course first and then the final grid.
Anyway, it's a minor point. Please continue. But we.
All right. Okay.
But that's,
Fine, yeah.
right. I don't know the answer.
No, me neither.
But noted, right?
Okay. So then, how is the way that we will do it in the pencil code? Of course, we must make it on a way that the code is structure doesn't change much. right? What is that? So,
Still jet lag and you're waking up in the night.
You do it to me, so.
So then what we were thinking about doing is having different matches of the same size. So then the array F will be F of X, Y, Z variable, and then mesh. In the sense, that's just the natural extension of the code, right? Several meshes of the same size, which we can treat in the same way that we have been doing the whole time with the code so far. But then there is a problem here. Everything works fine on the X direction. But if we want to make it parallel, then we might run into problems. I haven't done it yet, but then Tony says that he had tried it and he ran into troubles. Mainly due to the fact that what we will have, say, that we have here one mesh, right? That we make a parallel with this. If you put a nested grid in here, what we will have is that one of the processors will be calculating this one here and this one here, right? So then, how do we make the whole communication thing?
I mean, maybe it occurs to me just now. Maybe there's no global communication. All we have to communicate is still only boundary zones.
No, you need the initial condition for the finite patch. There's a whole finite patch at the beginning of the time step.
Wait a moment. I mean, so first of all, we just do this, yeah. So this is the full domain. Actually, where do we do all this?
Well, you
can't just evolve the finite patch from constant plus a boundary. It's going to be evolved from what was on the course.
Okay, so this stuff will be
from what is given from the last time step, and then the boundaries and something like that. Shouldn't that be enough?
Yeah, right. So, I mean, this is the close number one, right?
Basically, to interpolate the whole thing.
Oh, you're right.
You're right.
What did you say?
And this is close number 0. And this stays in process number 1. Even though the underlying mesh is in process 0. It doesn't matter, because all we need to communicate ever is, of course, boundary points. So, in other words, the point to
you only need to do boundary. You need to do global communication once, and then just the boundary thereafter.
Yes.
Because only the boundary actually evolves.
Right.
Yeah. It can be reduced a lot. There's communication to do, but it's certainly not.
No.
I'm not sure that I'm following what you're talking about.
So the finite, once the code starts running, this bit of the finite mesh, responsibility for this bit of the box belongs to this processor. But responsibility for this little bit of the calculation domain really does belong to this processor.
Yeah, that's true.
And the only, after the first interpolation, as Toby points out, the only thing that evolves is the only thing the course mesh needs to tell the finite mesh is how round it's going. So maybe you only have to do this 9 thick.
So you basically do redundant calculations then in that case, right? Because you want to coarse mesh also over the patches where the fine mesh is.
Yeah, but that's a normal problem.
That's not, you can skip, that you're right on, of course.
So there's not so much communication.
Yes, that's right.
Well, except of course you've got 9 ghost points, so actually, if we parallelize as we normally do to a problem size of, typical per processor problem size, 64 cubed.
Yeah.
Actually,
I
64 cubed
remember.
with 9 ghost points is kind of...
It's already high.
I remember why I put the 18 goes on and not 9.
Yes.
Because for one time step
You need two
of
time
the
steps.
course dimension, you need 2
Yes.
on the final.
Yes.
So it's 9 and 2.
It's a lot.
9 third time step of the final group. Does that make sense? So 18 ghost zones that need to be communicated. If you run something in which you don't need much points, 18 ghost cells is just too much. So
Well, it's going to be the whole processor, isn't it? It's going to have 1 point in the middle, isn't it?
yeah, that's more like that. So,
Well, what I mean, this is for the. I mean, if it becomes efficient on large enough meshes.
yeah.
So what I'm thinking of is meshes on the order of 256 cube, for example. So that means we have 256 cube meshes, for example, up to 6 times. Right? That would be a typical application. That would be affordable on most of the computers right now. And 18 relative to 256 is not.
That's not much.
36 probably.
Yeah.
Or is your factor 2 for the upper and lower?
No.
No.
36 for the two sides. But still, it's not outrageous, right?
10%.
It came down.
10% cube.
Yeah. But it is a thing that has
cube.
so many applications.
It's times 3. Not
No, because it's a volume, right? If you increase the length by 10%, you don't increase the volume of the same thing by 10% by adding that layer 50%.
You have cosloids, okay. Yeah, you have to multiply by n squared, maybe. That's what I mean. No, but otherwise times 3. 36 times 3 times n squared is the number of points in the ghost zones.
No, it's a volume.
So in the end, it's a thing that will cost, right? I mean, it will be computationally expensive, but it has such a broad. It has so many applications that I think that if we had it on the pencil code, that would be great. So I'd like to know what you guys think. If it's a thing that in your problems, if it would be useful, and how many of you would be using it? Because I will start coding it soon. So if I could get some help there too, I think that it would be a good thing.
So, for example, as far as I'm concerned, I could imagine, as I said already back then when we discussed this, that it could be useful even just for isotopic turbulence simulations. And everybody's looking, right?
Well, I think for the supernova stuff it would be perfect. I don't know how you might
so the isotopic turbulence is maybe the most outrageous idea, but there, of course,
shear layers.
I mean, in isotopic turbulence, you have a big volume of things, but everything is locally the same. So you want the highest resolution, but only on a small patch, and it doesn't really matter where the small patch is. You just want to have a represented point somewhere.
See what you're saying? Yeah, okay.
And so you, everything is isotopic. You want high resolution, and you just go to one particular point, and that's where you go down to the very smallest scale, and you just keep it fixed. What's wrong with that?
Well, if you assume that the entire fluid is completely coupled.
I mean, the problem, of course, is if you have massive advection going on. So suppose, for example, you have generated a thin flux tube in this high resolution thing, and it will, of course, leave the box, and then it will be lost because of lack of resolution. And likewise, if you have a coarse flux tube being advected into the fine mesh, it will have to do a lot of work because it will now be treated at much higher accuracy, of course. So the question is, how much do you gain from such a thing? But this is really a specific problem if you have a lot of advection.
I don't think there's any doubt you can use AMR for that.
It's not AMR. It's just MR.
Wow, yeah.
It wouldn't be that difficult. No, it's not supposed to be that. It's supposed
No,
to be
this mesh is absolutely, completely, totally fixed within the calculation plane.
from the beginning.
If you even let it move, of course, then you definitely do have to communicate everything all the time.
Okay, but it's not very similar then to the non-equidistant grid.
Do what?
We already have a non-equidistant grid.
Yes, but there are problems where you need dx, dy, dz. Ideally, you want dx, dy, dz all equal. Okay, in 3D, here's the problem with non-equidistant grid. The problem is that if I have a tall, thin box, and I spread out, and I do this in 256 cubes, but I use a non-equidistant grid, well, what I end up with is a grid which, yes, has got space out here, but then it's condensed up this way. But these lines going this way all have to be the same. The cross-section has to be the constant resolution. So now I'm going to end up with lots and lots this way. So now down here I've got these little high-resolution squares. But at a height, I've got these funny things that are very long, thin, and narrow. So although I've reduced this is the idea for doing a disk, right, with an atmosphere above and below. Right? So now I've got this really strange resolution that the 2D resolution is still just as high as it is down in the disk.
Why can't it be equidistant in the x direction and in your case in the z direction be condensed? Why does it have to be condensed? Why does it have to be so fine in the x direction? I do not understand that.
Because the number of lines in this, I mean, it's a rectangular mesh. Okay, I can pick this sheet up. I can do coordinate transforms to distort the sheet into any shape I want. But at the end of the day, the thing maps onto a rectangular mesh. So the number of lines in any direction must always be the same. Now, if I require there to be 256 lines, 256 mesh points across, then there must be 256 mesh points across up here.
So why do you want 256 mesh points across?
Well, because I want resolution.
If you use less than you still have a funny aspect to it, right? You can never determine the x grid in an equidistant way so that you don't get stretched boxes.
Why don't you want to do nested?
Unless you do nested, yes, but I mean in this non-equidistant grid.
What is the problem with having these problems?
Well, so I actually really only want, up here, what I really want is I want 1, 2, 3, 4 mesh points. I don't want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've got to calculate all of those mesh points, and all I wanted was 4. So I end up here with this x and y that I can't get rid of. I can't make this any smaller, higher up. That's why this is needed. Right? Okay. So that.
All right. Any other? But you were starting to ask who else would be using this. I mean, another application is of course dot formation, planet formation. That's what you're doing.
Yeah, that's what I'm doing.
So how about solar convection, light bridges? So you can do the light bridge at high resolution and the sunspot at not so high resolution, right?
I want
I think that there's loads of use for it. I thought about a different way of doing it that may or may not be of assistance, which would be, you don't really change the pencil code at all, but you make the pencil code capable of talking to itself. There's no reason, when you submit an MPI job, there is nothing that says that all the processes have to run the same program. I can actually submit an MPI job to, for example, 24 processes, and I can have 8 of them solve one problem, 8 of them solve another, and 8 of them solve the other. Oh, look, I've got 3 meshes.
These are these so-called embarrassing parallel problems. These are the so-called embarrassingly parallel problems.
But that's precisely this problem. So one thing you could do is you could then solve these 3 problems and do a nested grid where my communication between pencil code problems is just the boundary. Because this is a complete pencil code problem here. It's totally evolved. It's just at time step twice as fast. And there's got to be some communication at time step. But the other possibility is in this stratified disk thing. In the odd occasion where actually I just want to do this in one direction, I can, as Toby mentioned, there's a problem that you end up double calculating where the nested grid is in this. But if you do communicated pencil code, then you can do a low resolution mesh, an overlap region for the boundary, a high resolution mesh, an overlap region, and another pencil code problem. So now I really don't solve in between. I just have 3 pencil code problems that talk to each other. In fact, the pencil code doesn't change at all. The only thing that changed is bound cons x, bound cons y, which now has to be capable of communicating.
Okay, if you have a more complicated
they have the same
grid geometry, that's not, I mean, if you don't have a slab where you have a high resolution on one hand and low resolution on the other hand, but like a square where you want to have high resolution in the middle, then that doesn't really...
That's what I just said. It lets you do things in all these slab geometries. In fact, of course, there's absolutely no reason I can't put a low resolution here, and a low resolution here, and a low resolution here, and a low resolution here. Let's do 9 pencil code problems.
Isn't that what we're doing already?
No, you're calculating the thing right in the middle. And this,
No. I mean,
this still has this array, of course.
No, it had now a pencil code. In principle, we have, when we run on 128 processors, we have 128 low resolution problems.
Indeed. So now what we do, but this is the point. This is exactly my point. That's exactly it. Now, one of the processors. Oh look. Except we have to be able to do this. Maybe we have to do this in X as well. Although if we only ever want to do it in X and in Z and Y and Z, the entire thing is there. The only problem is that we need to have an MPI I send receive, which is capable of doing interpolation en route.
Yeah, but wait a minute. I mean, you want to, the high resolution, of course, takes longer. You want to, it takes longer time, right? And all the other processors don't want to wait. So how do you avoid that? You've got to make sure that the low resolution domains are taking the same amount of time as the high resolution.
Okay. So I submit. I mean, I'm suggesting this is an idea. Please don't be sort of critical of it. It's a sort of.
No, actually, there's a misunderstanding. I think when I said we are doing this already, that's not really true. So we would be doing the same thing if the pencil code with multiple processors, so with multiple, as it looks like, with multiple processors, was actually running on one processor in serial, and not concurrently. So in other words, we say, okay, the clock starts to tick. Now processor 0 runs for the first second and does its job. Now processor 1 runs for 1 second, and so forth. So after 128 seconds, all the processors have done their job, in everything in serial, but in separate parts of the domain, of course. That would be sort of cache efficient in some sense. Okay, and so it's a single processor business. It has nothing to do with parallelization.
Yes, but how
you decompose the domain into course.
But of course, everything is only efficient if the processors take the same amount of time for doing the serial process.
That's a low balancing problem.
They don't necessarily do this with varying resolution, right?
The problem is really that at high resolution we have 256 mesh points. At high resolution we have a number of processors, and so forth. Every time we have the same processors. So
yeah, okay, but that's not what Sony's talking about, right?
That's right. So we have at time 0, at time 1, and at time 2 we have always the same identical problems, of course. I mean the load wise.
Yeah, but that's just a picture where you have like processor 1 has the upper right corner in the lowest resolution mesh, and the upper right corner in the next higher resolution mesh, and the upper right corner in the highest resolution mesh. But that's not what Tony's talking about, right?
Well, is that not what it is?
It's first, what you're saying, it's only a load balancing problem. It's got nothing to do with the code at all. So for a start, I haven't said how I parallelize each of these problems. I could use twice as many processors in each direction to parallelize this.
Yes.
So I could parallelize, so I might use one processor for each of these, but I use 4 processors here.
Right.
As long as it knows where to send that this bit goes to this processor, and this bit goes from, this is a parallelized thing in here, and it's load balanced. Moreover, I mean, the reason I thought of this is because it doesn't involve significant changes to the code at all. I mean, you don't, for example, have to go through every routine and change the F array. The F array doesn't change at all. Moreover, there's this situation that Wlad and Jeff and I have discussed, that actually, in almost all of our problems, the global geometry of the mesh and the refined geometry of the mesh are not necessarily, or are not usually the same thing. And in the nested mesh, using this big F array with my mesh here, all patches have to be the same size. All meshes, if you pick 256 cube, that's what you have. In this situation, if I decide that actually I only want to have this thin sliver on the side here, as long as these boundaries meet up, the whole thing works fine. So now I can have my interstellar disk with my long, thin, high-resolution slab. I can have my tall, thin columns, and have a square mesh everywhere. So in some ways, this is more general and requires less pencil code coding, but it does require you to think outside the box a little. You've got to really sort of think, because like the load balancing problem has to be handled automatically.
So we discussed this at some point. I think, didn't we? We should consider this possibility.